All right, hello. We're going to look now at section 4.3 on primes or prime numbers and greatest common divisors. Okay, so the definition of prime, to be a prime number, says an integer p is a prime if p is greater than 1 and the only positive factors of p are 1 and p itself. For example, 13. The only positive factors of 13 are 1 and 13, because you can only write it as 1 times 13. So if an integer is greater than 1 and is not prime, then it is called composite. Or n is composite if and only if there exists an a such that a divides n and a is in between 1 and n. So, for example, the number 12. Okay, does there exist a factor of 12 that's in between 1 and 12? Well, yes. 2 is a factor of 12, and it's in between 1 and 12. 3 or 4 or 6, those are all factors of 12 that are in between 1 and 12. But 13, that is prime because there's no factors of 13 other than 1 and 13. Now, the fundamental theorem of arithmetic says every integer greater than 1 can be written uniquely as a prime, or as a product of 2 or more primes, where the prime factors are written in order of non-decreasing size. So in other words, for every number, it's either a prime number or we can break it up into the product of all prime numbers. If we just continue to break up the numbers as far as we can go, we will eventually reach that it's the product of a bunch of primes. For example, 540. You could break that up into 10 times 54. Of course, 10 is composite, so it breaks up into 2 times 5, and 54 breaks up into 6 times 9. But then 6 can be broken up into 2 times 3, and 9, of course, is 3 times 3. So if we arrange the factors that result after we break up all the composite numbers into primes and put them in order, there's 2 2s, there's 3 3s, and a 5. And this is the product of all of that equals the original number 540. And this is what we call the unique prime factorization of 540. Now we say it's unique, just like a fingerprint is unique to us. This is unique to that number 540. There's no other number that has that same prime factorization. Okay. Now, a theorem given here on this slide helps us to know when we can stop in looking for factors of a number. The theorem says if n is a composite integer, then n has a prime divisor less than or equal to the square root of n. Okay? So you might want to look at the proof in the textbook, but you don't have to. So we can use this theorem to perform what is termed as trial division. We do this to try to find if an integer is prime or not. So for example, is 539 a prime number? Show how you know or do not know this. First of all, you figure out what is the square root of 539. So you can take your calculator and do the square root of 539, and it'll be 23.216, etc., etc., etc. So that what the theorem says now is that if n is a composite number, if 539 is composite, then it will have a prime divisor less than or equal to that square root number. So we ought to be able to, if 539 is composite, find a factor of it before we get to 23.216. In other words, up to 23. So then you start testing to see if 2 is a factor. Well, 2 is not, because the 539 is an odd number, so obviously that's not going to be the case. Then we can look at, okay, there's a few divisibility facts here. Since 539 is odd, then obviously 2 doesn't divide into it. Also, the sum of the digits is 17, which is not a multiple of 3. If the sum of the digits had been 18, then I know that the number would have been divisible by 3. But because the sum of the digits is 17, then the number is not divisible by 3. And because the last digit is not a 5 or a 0, we know that it's not divisible by 2, 3, or 5. Okay? So now all we have to test is 7, 11, 13, 17, 19, or 23. Now as soon as you test 7, you find that 539 divided by 7 comes out even to 77. So you see that 539 is not a prime number. But if you had tested all those numbers, 7, 11, 13, 17, 19, and 23, and all those prime numbers did not work, then you would know that 539 is prime. But because we found that 7 goes into it, it's not prime, it's composite. Now the last line gives the prime factorization, because 539 is 7 times 77, which breaks up into 7 times 7 times 11. So that is the prime factorization of that number. Now the Sieve of Eratosthenes was a method of finding all prime numbers less than a given number, n, by beginning with a list of all the integers up to n, and then removing multiples of the prime numbers less than n, a square root of n. So table 1 on page 260 shows how to find all the primes less than 100 by eliminating multiples of 2, 3, 5, and 7. As soon as you do that, you're done, because what's the square root of 100? It's 10. So you only have to look at all the prime numbers less than 10. And those are 2, 3, 5, and 7. So you can look at that on page 260. Now, it is true that the further up you go in the numbers, prime numbers get more and more rare. At first, 2, 3, 5, 7, there's 4 prime numbers, all less than 8. But as you go up higher and higher, they get more and more rare. Okay. Now, theorem 3, though, proves that there are an infinite number of primes. And the way it proves this is that it assumes that there are a finite number, like that there's a last prime number, but then it arrives at a contradiction of that. So it must mean that the prime numbers just keep going on and on and on and on. Now, Mersenne primes, named after a French monk, these are primes of the form 2 to the p power minus 1, where p is also a prime number. For example, the number 31 is a Mersenne prime, because if we choose p equal 5, okay, so what's 2 to the 5th power? Well, 2 to the 5th power is 32, and 32 minus 1 is 31. So 31 we call a Mersenne prime. 7 is a Mersenne prime, because if p equals 3, then 2 to the third power is 8, and 8 minus 1 is 7. So any number that fits or comes from p being a prime number and plugging into that formula, that's called a Mersenne prime. Theorem 4, the prime number theorem, basically helps us know how frequent prime numbers are. We said that as you go further and further up, that the frequency of prime numbers decreases, or in other words, they get more and more rare. Well, this gives a mathematical statement to that, and it says the ratio of the number of primes not exceeding some number x to the quantity x divided by the natural log of x, ln x. That ratio will approach 1. So in other words, the number of prime numbers less than x will get closer and closer to this ratio of x over ln x as x gets larger and larger. So I'm not sure if you have to do anything like a homework problem from that, but it's just a fact about primes. Here's some other what are called open conjectures about primes. This means something that mathematicians have not yet been able to prove, but they think is probably true. Now, mathematicians have not been able to develop a formula that always generates prime numbers. They would like to have a formula that will always generate prime numbers, but they don't have such a formula. A lot of formulas that they thought were able to generate prime numbers, as many as we wanted, actually do not. Like here's an example, the function f of n equals n squared minus n plus 41. That will generate prime numbers if you plug in n is 1, n is 2, n is 3, n is 4, all the way till n is 40. Okay? But as soon as, does it continue to do so? No. If you try in n equal 41, it will not work. So it might work 40 times, and then on that 41st time, it fails and does not generate a prime number. Now, Goldbach's conjecture has never been proven, but a lot of mathematicians believe it is true. But they have tried to prove it, and they have failed. The original conjecture by Goldbach said that every odd integer greater than 5 can be written as a sum of 3 prime numbers. So they believe that's true, but they can't prove it. Now, a great mathematician, Euler, proved that this is the same as saying that every even integer greater than 2 is the sum of 2 primes. If you can prove what Euler characterized the conjecture as, that every even integer greater than 2 is the sum of 2 primes, then you can easily know that Goldbach's conjecture that every odd integer greater than 5 can be written as a sum of 3 primes. But no one has been able to prove either Goldbach's original way he wrote it or Euler's alternative way. All right, so let's talk about greatest common divisors and least common multiples. Okay, so here's the definition of the greatest common divisor. Let a and b be integers, not both 0. So you need 2 integers so that at least one of them is not 0. The largest integer d, such that d divides a and d divides b, is called the greatest common divisor of a and b. So it's just the largest divisor that divides both of the numbers. Now this greatest common divisor of a and b is denoted as GCD parentheses a comma b end parentheses. So it's simply the greatest number that divides into both of the numbers. Question: is it possible that there is no greatest common divisor? Does every two numbers have a greatest common divisor? Well, considering that 1 will divide in evenly into both a and into b, well, then at least the number 1 is a common divisor. And if so, if there's no other divisors, then that might be the greatest common divisor. So even if you think that two numbers don't have any common divisors, then 1 is a common divisor. And so this two numbers will always have a greatest common divisor. Okay, here's an example. What is the greatest common divisor, the GCD, of 20 and 84? All right. Well, the common divisors of 20 and 84 are 1, because 1 divides into 20 and 1 divides into 84. Also, 2 divides into 20 and 2 divides into 84. And 4 divides into 20 and 4 divides into 84. So all of those numbers divide into both 20 and 84. And the largest or the greatest one is 4. So then the greatest common divisor of 20 and 84 is 4. All right. Now there is another way that we could have done that, and we're going to be looking at that. Now first, before we look at a way of calculating the greatest common divisor, let's look at what's called relatively prime. Integers a and b are relatively prime if their greatest common divisor is 1. So in other words, they don't have any other common divisors besides 1. Of course, 1 will always be a divisor of any number, but if the greatest common divisor of the two numbers is 1, that means they don't have any other divisors besides 1. And we call those two numbers relatively prime, like 7 and 9. Now, I know 9 is not a prime number, but the divisors of 7 are 1 and 7, and the divisors of 9 are 1, 3, and 9. The only divisor that's common to both of those numbers is 1. And if the greatest common divisor is 1, then we call them relatively prime. Okay? Now, you can also have a whole set of numbers that are relatively prime. Whole bunch. Let's say you had a whole bunch of numbers like 22 and 7 and 9. Well, the divisors of 22 are 1, 2, and 11. The divisor of 7 are 1 and 7, and the divisors of 9 are 1, 3, and 9. But the only divisor that's common to all of them is 1. And so that's what this is saying. Now it's called, okay, for a group of integers, a1, a2, a3, all the way to an, they are called pairwise relatively prime if the greatest common divisor of two of them is equal to 1. So any two ones you want to pair up, if the greatest common divisor of those two numbers is 1, then they're relatively prime. So if that's the case for any two matchups of the integers in this list, then they're all called pairwise relatively prime. Okay? So like I said, 22, 7, and 9, would be a set of pairwise relatively prime numbers. So if you take any two of them, let's say we take 22 and 7, well, there's no common factors except for 1, so they're relatively prime. Let's say we take 7 and 9, well, they're relatively prime because the greatest common divisor of those is 1. And also 22 and 9. 22 and 9, the only common factor is 1 between them, and so the greatest common factor is 1, so they're relatively prime. So we've tried all the pairing up of them, and so they're pairwise relatively prime. Same goes for these numbers 26, 33, and 35. The greatest common divisor of 26 and 33 is 1. The greatest common divisor of 33 and 35 is 1. And the greatest common divisor of 26 and 35 is 1. And so these are called pairwise relatively prime numbers. Okay? Now, at the bottom of the page, you have given to you a way to find the greatest common divisor of two numbers. Okay? So the greatest common divisor of A and B is a prime number P1 to the power of the minimum of A1, B1, P2, the minimum of A2, B2, etc., all the way to P sub n, all right, where min finds the minimum of the exponents from A and B on common prime numbers P1, P2, Pn. So what we do is find what's called the prime factorization of each of the two numbers of A and of B, and then you look for any common primes and you take the minimum of the exponents on those common primes. And you'll see what I mean when we look at an example of this. But you just basically write out the numbers as the prime factorization, in other words, the prime numbers to an exponents. So if there's one prime number, like there's 1 7 in there, you'd go 7 to the first power. But if there's, 2 11s, let's say it's 11 times 11, you'd have to go 11 to the second power. Let's look at an example. Well, I'm sorry, we're going to look at least common multiple first, and then we'll look at an example. So the least common multiple of the positive integers A and B is the smallest positive integer that is divisible by both A and B. The least common multiple of A and B is denoted as LCM A comma B in parentheses. Okay, so this gives a way to find the least common multiple of two numbers. So least common multiple of A and B, and we're going to take the prime numbers of all the primes that you find in either A's prime factorization or in B's prime factorization. Okay, and then you're going to take the maximum of the exponents of those. So you take the first prime number to the maximum exponent that you find in the A and the B, and then the second prime number to the maximum exponent, the third prime number to the maximum exponent, and this is done for all the primes that are in either number. Now that's important. You've got to include all the primes that are found in either number to the maximum exponent that they have in either number. But greatest common divisor, though, that was the minimum of the numbers that are in common. Okay, so here's an example. It says find the GCD and the LCM of 60 and 72. So first we find the prime factorizations of both numbers. So 60 is 2 squared times 3 times 5. You just have 1 3 and 1 5. 72 is 2 to the third power times 3 to the second power. Now, it seems strange, but with the greatest common divisor, you're taking the minimal, the minimum of the exponents of things that are in both numbers. So it has to be prime numbers that are in both prime factorizations, and the only numbers that are in both prime factorizations are 2 and 3. The 5 is not in both. And then we're going to take the lowest of the exponents. Now, this is 2 squared. Over here you have 2 to the third, so the minimum of that is 2 to the second. So you take 2 to the second power, and then as far as the 3's, you have 3 to the first and 3 to the second, so the least of those two, or the minimum of those two, is 3 to the first. So it's ironic, but the greatest common factor takes the least of the prime numbers. Now, the reason that's the case is, to be a factor, it has to go in evenly into both numbers. And we can't add more 2's, for example, than there is in the number that has the least, because it has to go into both numbers. So it's the one that has the least 2's that limits you to how many you can take. Okay? So 2 to the second times 3, which is 12. So the greatest common factor of 60 and 72 is 12. Now the least common multiple, here we got to take everything that occurs to the maximum exponent of what it occurs. So, all right, we need the 2, and we're going to take it to the third power, so 2 to the third power. We need a 3, but what's the highest exponent on the 3? Well, it's 2, because we're going to use the maximum exponent. So 3 to the second power, and then 5 to the first power. So we got to include all the things that we see in either number to the highest exponent that they occur. And that's called the least common multiple. Now, the reason the least common multiple is larger is because it's a multiple of both those numbers. So we are looking for larger numbers that are multiples of both 60 and 72, and 360 is a multiple of 60, but also 360 is a multiple of 72. So it's the least common multiple of the two. All right. But it's ironic that for a least common multiple, you're taking the maximum that occurs. So here's another example. Find the GCD and the LCM of 140 and 600. So the prime factorization of 140 is 2 squared, 5 to the first, 7 to the first. The prime factorization of 600 is 2 to the third, 3 to the first, 5 to the second. Now we can also express these using powers of 0 if it doesn't have any of that term in there. Why would we do this? Well, you're seeing what the minimum and the maximum is, and sometimes the minimum of the two is 0. You'll see what I mean in a minute. So this, I wrote the 2 squared, 5 to the first, 7 to the first, but I added a 3 to the 0 power because there's no 3's in there. And in the case of 600, I added a 7 to the 0 power because this has a 7. This doesn't have a 7. So it's kind of emphasizing how many 7's that the two numbers have. So the greatest common factor of 140 and 600 would be 2 to the second, 5 to the first, 3 to the 0, and 7 to the 0. But we don't write them if they're, to the 0 power. So we're taking the minimum of the exponents, and for the numbers 3 and 7, the minimum exponent is 0, so we don't need to write them. The LCM we take the maximum of the exponents. So the 2 to the third power, because 3 is the maximum power on the 2. 3 to the first power, because 1 is the maximum exponent on the 3. Over here we have 3 to the 0. And then 5 to the second power, because 5 or 2 is the highest power on the 5. And then 7 to the first power. All right. So we got to include the highest of all the exponents. So if you multiply that out, you get 4,200. So the greatest common divisor is 20, but the greatest or least common multiple is 4,200. Now another useful theorem in regards to greatest common factor and least common multiple is theorem 5. Let a and b be positive integers, then a times b is equal to the greatest common divisor of a and b times the least common multiple of a and b. Now you can verify this with the example right above. If we multiplied 140 times 600, we get 84,000. Okay? But if we multiply the greatest common divisor, which is 20, times the least common multiple, which is 4,200, we also get 84,000. So this will be true all the time, that the product of the numbers equals the product of their greatest common divisor and their least common multiple. Interesting, eh? There's a reason for that. Now, an important algorithm that we want to learn, and we're going to use it in a couple different cases, is called the Euclidean algorithm. And this was invented by Euclid, the great mathematician Euclid, way back thousands of years ago. But the algorithm gives an efficient way to find the greatest common divisor for two integers a and b. Okay, so it's a way where we don't have to figure out the prime factorizations of the two numbers and do it that way. We can do it another way. So suppose that you had to find the greatest common divisor of 390 and 924. So this is what you do. You successively divide the numbers as follows. First, over here on the far left, you divide 390 into 924. So you just take the smaller number into the larger number, and it goes into it 2 times with a remainder of 144. Okay? Then you take that remainder and divide it into the smaller of the two numbers, 390 in this case. So you divide 144 into 390, and you get 2 remainder 102. Now you don't care about the quotients, you just care about the remainders. Okay, so anyway, so you get a remainder of 102. All right, so then you divide 102 into the 144. So you swing it over here and put it there. So 102 into 144. It goes into it 1 time with a remainder of 42. All right, now we'll go 42 into 102. And it goes into it twice with a remainder of 18. Then you go 18 into 42, and then that goes into it 2 times with a remainder of 6. And then you take 6 and divide it into 18, and it goes into it 3 times with a remainder of 0. Okay? Now, according to the Euclidean algorithm, the last non-zero remainder, which in this case is 6, is going to be the GCD, or the greatest common divisor of the two original numbers. So that's all you got to do is, keep doing this and figuring out the remainders. the last non-zero remainder. Now you'll have to go all the way to the end until you get a remainder of 0, because you won't know to stop until that point. And then you back up to the last non-zero remainder, and that's your GCD. Okay. Now the Euclidean algorithm is written as a computer algorithm in algorithm 1 on page 269. Now I went ahead and brought this into the slide here. Euclidean algorithm, it receives two integers, a and b, so that inputs it into the algorithm, and then it lets the number x equal the first number a and the number y be b. See, you don't want to change what a and b are, but we're going to change what x and y are in the procedure. Now it goes all the while y is not 0. So it's going to do this all the time until y is not 0. Or I'm sorry, all the time while y is not 0. So first it lets r be the remainder when x is divided by y. And that's what x mod y does. It finds the remainder when x is divided into y. No, I'm sorry, when y is divided into x. Then it sets x equal to y and y equal to the remainder. So it's always setting that other number, that lower number, into the remainder. And then it goes back up and does it again. R becomes equal to x mod y, and then x will equal to y, and then y will equal to r. So it just keeps doing this all until it gets a 0 remainder, because once the remainder is 0, it'll stop. And then it'll return whatever x is. And whatever x is will be the last non-zero remainder. Okay? Because when y was 0, it didn't reach this line here to change x to 0. So x is still what it was before, and that's the last non-zero remainder. Okay? Now one more helpful thing, there's a lemma. Now a lemma is simply a little theorem that doesn't have any significance of its own, but it's useful to help us prove other things that are more important and useful. So a lemma is just a little theorem that nobody really cares about what that says, but it's helpful to prove something else. So this lemma says that if a equals b times a quotient plus a remainder, so in other words, when you divide a by b, q is the quotient and r is the remainder, then the greatest common divisor of a and b equals the same as the greatest common divisor of b and the remainder. Okay? Interesting. The greatest common divisor of a and b is the same as the greatest common divisor of b and the remainder when a is divided by b. So this is used in a proof of the Euclidean algorithm, and seen in example 16 on page 268. So let's look at another important aspect of greatest common divisor. But first, we need to know what a linear combination is. A linear combination. So a linear combination of a and b, this is an example, 3a minus 5b. So basically it's any integer in front of a and any integer in front of b, and that combined into one combination. Another example is a plus 7b. So you have a coefficient, in this case it would be a 1a plus 7b. So the coefficients in front of A and B could be positive or negative integers, but it's a linear combination of A and B. Now it's possible that the coefficients are 0 too, but that's not going to be something we're going to be looking at, but it's possible to have the coefficient be 0 for one of them. All right. Now, theorem 6 is an important result. It's Bezout's theorem, and it says if A and B are positive integers, then there exists integers s and t such that the greatest common divisor of A and B equals a linear combination of A and B. So s and t are the coefficients in front of A and B in the linear combination. So what this is saying is that we can figure out there exists an coefficients on the A and the B so that the greatest common divisor is equal to that linear combination. Or in other words here in the parentheses, this means that the greatest common divisor of A and B can be written as a linear combination of A and B. Now these coefficients are called Bezout coefficients, and the equation is called Bezout's identity. All right. So this equation that GCD of A and B is equal to SA plus TB, where S and T are two integers, has those names. Okay, has that name of Bezout's identity. Now example 17 on page 270 shows how to use the Euclidean algorithm and working backwards from what the Euclidean algorithm gives you to find the Bezout coefficients. Bezout coefficients. All right, so let's look at another example, but you can look at that example in the book if you'd like. Okay, I'm sorry. We'll look at this in a minute. Now, some other lemmas and a theorem. Lemma 2 and 3 can be used to prove the uniqueness of prime factorizations for numbers, as well as another result that we're going to look at here. Example of something that is an issue first, and then we'll look at a theorem that'll help us out with that. So suppose we have the congruence 6 is congruent to 18 mod 12. Now we know that that's true because 12 does divide into the difference of 18 and 6. 18 minus 6 is 12, and 12 divides into 12. So we know that 6 is congruent to 18 mod 12. So could we divide both sides of this congruence by 6? I mean, that would make it more simple, right? Well, no, because if we did, 6 divided by 6 gives you 1 on the left side, and 18 divided by 6 gives you 3 on the right side. And it's not true that 1 is congruent to 3 mod 12. How do you know this? Because 12 doesn't divide into the difference of 3 and 1. The difference of 3 and 1 is 2. 12 doesn't divide into 2. So it's not true. So we can see in this case, we cannot divide both sides by 6. Okay? Well, what is the cases where you could divide both sides by a number? What enables you to divide a congruence on both sides? Well, theorem 7 tells you the case that you can. Let m be a positive integer, and let a, b, and c be integers. If AC is congruent to BC, mod m, and here's the key, the greatest common divisor of C and M is 1. In other words, they're relatively prime. If the number you're dividing by and the mod the modulus, m, are relatively prime. In other words, the greatest common divisor of them is 1. Then you can divide both sides by c, and you get A congruent to B mod m. And so study this, and we'll look at the next lesson in a moment.